This video has to do with laboratory number 2 for BBE 3012. In this laboratory we're going to be making velocity and pressure measurements for different systems. We're going to be looking at flow through an orifice. We're going to be looking at flow for free jet analysis, that is. We'll be looking at flow through an orifice where there's pressurized flow on both sides of the opening, and then we'll be looking at flow in open channel, and lastly we'll be looking at flow through pipes. In the first analysis we're going to be looking at free flow out of a jet coming out of a small glass reservoir, as shown here. We've got this container that's got a outlet, and I'll point that out here. So here's the container and there's the outlet. We got a valve on the outlet. I'm going to be using these 500 milliliter containers to measure flows coming out of these reservoirs. You use this meter stick here to measure the depth of water within the container, within the reservoir. So what you're going to do is you're going to fill the reservoir to about 80% of its height or its volume, and that's with the valve closed, and then you'll open up the valve and water of course will come out. You're going to be timing the time. You're going to be determining the time that it requires for 500 milliliters to discharge out of the reservoir, and you're going to do this repeatedly while the water level in the reservoir drops. And of course, as it drops, the discharge will be decreasing because the head within the reservoir will be decreasing. You'll continue to make measurements until the water level in the reservoir reaches about 10%, somewhere down here, of its volume. From the analysis, or from the data that you'll be collecting, you're going to be determining the discharge coefficient for the free jet. You'll recall that the discharge in a well, let's say the velocity coming out of a jet, free jet, is given by this relationship, square root of 2gh, and the discharge, which we'll actually be measuring, is a coefficient, contraction coefficient, multiplied times the area of the opening times the square root of 2gh. So what you'll be determining in this experiment is the contraction coefficient. Here I refer to it as being discharge coefficient, but I'm also mean there the contraction coefficient. The second part of the experiment, you're going to be measuring water levels, pressures, and also water levels in a open channel. A photo of the open channel is shown here. And what we'll be doing is this has a reservoir associated with it, and basically what happens is that water comes up out of this reservoir up into the bottom underneath the channel. This is the channel bottom right there. Comes up and passes through an orifice that's located right about here, and then enters into this container on the left hand side. Here is a gate, and that gate can be raised or lowered. So this is essentially in here a reservoir. Water flows underneath this gate over the top of this surface, and it kind of builds up and it will flow along here and then discharge down this way, and that goes back into the reservoir and then gets fed back into the back through the orifice. So it's a recirculating system. What we'll be doing here is we'll be setting 3 different flow rates by adjusting the opening of the orifice. And there's a crank on the other side, which may not be visible. It's located right here on the other side of the of this laboratory model. That crank can be opened up. It opens up the orifice and thereby lets either more or less water flow into this reservoir here, and so you get less flow coming down the channel. On the other side of this model, there's a manometer that you'll be measuring. It's a differential manometer. You'll be measuring the difference in water level in the manometer to determine the pressure loss across the orifice. With an orifice, basically what we've got is something like this. Here, if I can move this down, try to fit something in here. Here's the orifice. Water is flowing through here, and we'll have a pressure P1 on the one side, we'll have a pressure P2 on the other side, and those two pressures will be connected, or the water on each side of that orifice will be connected to a differential manometer that you'll measure, and that's calibrated then for determining what the discharge is through the orifice. Alright, so then what we'll do is at each one of those flow level measurements, we're going to have you, we're going to do 3 different flow levels. And for the highest flow level measurement, you're going to determine the elevation of the water surface at 5 locations, equally spaced locations along the channel. Measure your distance to those locations from the left-hand side here. Do that at 5 different locations. You'll know then what the depth of water is, and I know that what you'll see is that the water is going to be fluctuating up and down. The depth will be because of turbulence and so on, but you should try to approximate the height of that water surface, somewhat of an average depth for that water surface at any given location, but you'll have 5 measurements of that water level. Then after those measurements are made, we're going to place in here a weir. That weir is going to have a shape like this. Of course, that'll back water up behind the weir, and water is going to be flowing over the weir. You'll be measuring the water level upstream of that weir, and we'll be calculating it, because we'll know what the discharge is over the weir. We'll be able to calculate what the discharge coefficient is for the weir. In addition to this, on your diagram you'll see that there's a Pitot tube located right at this location. It's hard to see it now because I've kind of covered it over. I'm going to try to get it back here so we can actually see it. Okay, Pitot tube is located right here. Pitot tube is located right there. That'll be submerged below the water surface to some depth, and this is connected to it's connected to a manometer, and you'll measure the water level in the manometer. There are actually 2 manometers that you need measurement on. One of them is associated with the depth of water in the channel, The other one is the actual pressure associated with the stagnation point right here at the upstream end of the Pitot tube. So you'll be making measurement of both of those, and from that you'll be able to calculate a velocity for the flow, knowing the dynamic pressure. Lastly, what we'll be doing is we'll be making measurement of flow and pressure through pipes. And we constructed a small pipe network last year. It says this past summer. It was actually the summer before. So this was the summer of 2014 when this was built. And what we have here are 5 different pipes. One of them has is not a uniform diameter pipe. It's got 2 sections that are same diameter, and then one portion that's in between that's a different diameter. Then we have other pipes that are of different diameter. And upstream and downstream of some of these points we've got small, we've got connections so that we can actually measure the water pressures at these points that you see here. And we do that by connecting these manometers to these connections, and with those we're able to measure the water pressures. Brad Hansen is going to show you actually how to make those water pressure measurements. Now we're going to do this at 3 different flow levels, and the flow levels are controlled. Brad Hansen will be setting those flow levels. We'll be doing it at 3 different flow levels, and what we're going to do is we want to make measurements for the pressures for all these connections that you're seeing. That does seem like an awful lot of work. So what we're going to do is we're going to have each team be responsible to make measurements on just one set of the devices that we see here. And we have elbows, we got non-uniform pipes, we've got some uniform pipes but different diameters and so forth, and that would take too long for each team to make measurements on all of those. So what we'll have is we'll have each team make measurements on just one set of the devices for all 3 flow rates, and that'll reduce the amount of work that's required. Now you're going to want to make very good measurements because you're going to be sharing your data with all teams. So each team will share data with the other teams, and you don't want to shortchange any of the teams by taking poor data. This is an illustration of the flow control system. So the flow going through that pipe system, which is pipe system is located over here, off of here, is controlled by the valves and the piping that's shown here.